Namaste, friends. Welcome to today's explainer on the architecture of memory. We are going to jump right into a really beautiful papercraft journey today. We're going to literally peel back those abstract layers of code and see what the physical reality of computation actually looks like. It's quite something. So let's begin with our protagonist, Arjun. Just picture him sitting there in his lovingly crafted paper room, right? The soft glow of the computer screen is lighting up his face, and his whole world looks like this intricate folding pop-up book. He's sitting there typing this profound question into his keyboard, a question I think every curious mind eventually asks once they start programming. He types, "Where does my data go when a program runs?" And you know, it's a brilliant question, because understanding this, it's the fundamental bridge between just writing code and actually mastering how a computer operates. Well, to answer Arjun, we first have to understand how a computer organizes its physical space. So let's zoom out a bit. Imagine our papercraft world expanding out into this incredibly long, winding street lined with literally thousands of perfectly folded little houses. This is computer memory in action. Just like a row of houses on your local street, every single byte of temporary storage has its own specific, highly unique address, usually written out in hex. The computer's CPU uses these specific addresses to find exactly what it needs, grabbing those ones and zeros of machine language without ever getting lost.
Okay, let's really dive into this. Imagine zooming in on just one single paper house on this massive street. As we get closer, watch how it just miraculously unfolds. It expands, stretching up into this towering, magnificent 5-story building. This building right here, that represents a compiled program sitting in memory. Whenever you write a program in a high-level language, like C, and you compile it, the computer creates this exact structural footprint.
Now take a look at the structure of this newly formed building. A compiled program's memory is always divided into 5 distinct segments, or floors. Starting right from the bottom up, we have the text segment. Sometimes people call that the code segment. Then right above it, the data segment, the BSS segment, the heap segment, and finally, perched at the very top, the stack segment. And every single one of these floors has a highly specific, totally crucial purpose to make sure your program runs flawlessly. Let's check out the foundation first. The bottom 3 floors of our papercraft building, so that's text, data, and BSS, they are entirely rigid. They are completely fixed in size the exact moment the program is compiled. You can think of them like the solid concrete base of our structure. Nothing down here changes in its overall capacity, and that provides this absolute stability for all the crazy dynamic operations that are going to happen on the floors above. Right on the ground floor, we find the text segment. This is the home of your assembled machine language instructions. The processor's instruction pointer, you might know it as the EIP register, points right here, executing your code step by step. But here's a super fascinating detail. It is completely read-only. Why? Well, to prevent anyone, or any rogue process, from accidentally or maliciously modifying the program's core instructions. It is locked down tight. If you even try to write on this paper, the program will instantly throw a segmentation fault and shut the whole thing down. No exceptions. Moving on up to the second and third floors, we run into the data and BSS segments. These floors are dedicated entirely to the program's global and static variables. You know, the variables that have to stick around for the entire life of the program. The data floor holds the initialized variables. These are the ones that were already given a specific value right there in your source code. And then, directly above it, the BSS floor holds their uninitialized counterparts. They are kept neatly separated, which keeps our whole building perfectly organized and highly memory efficient.
And this brilliantly illustrates the true climax of our building's architecture. We've finally left those rigid lower levels and entered the dynamic space. The heap segment actually grows downwards from the roof, reaching toward the higher memory addresses. Meanwhile, the stack segment grows upwards from the basement, reaching toward the lower memory addresses. It is this totally breathtaking dance of expanding and contracting paper happening live as the program runs.
So what does this all mean? The absolutely crucial point here is the contrast between our static and dynamic floors. While those bottom floors are completely frozen in size, the top floors are incredibly flexible. They stretch, they shrink. By growing toward each other dynamically, the computer brilliantly minimizes any wasted space. Like, if the stack needs to be a bit smaller for a moment, the heap can just grow larger to borrow that space, and vice versa. It's honestly a masterpiece of architectural efficiency.
Let's take a closer look at the heap floor. This is the sprawling open space that the programmer directly controls. Imagine it like a grand hall where allocator algorithms act kind of like event managers. Using functions like malloc in C, a programmer can literally reserve blocks of memory on the fly.
The allocator finds the space, reserves it, and hands you back a pointer to it. But when the program is done, it absolutely must use the free function to release that paper back to the hall. It is entirely dynamic, and remember, its growth moves downward toward those higher memory addresses. Now looking up, let's see how that compares to the stack segment. If the heap is this grand programmer-controlled hall, the stack is more like a fast-paced temporary scratch pad that's managed entirely automatically by the compiler. Whenever a program calls a function, it uses the stack to store local function variables and execution context. It bundles all this information into neat little paper packets called stack frames. And as it changes in size, it grows upward toward those lower memory addresses.
To really grasp how these stack frames are organized, we have to talk about the stack's golden rule: first in, last out, or FILO. Picture a beautiful papercraft string with a really sturdy knot at the very end. If you slide or push a bead onto it and then you push a second bead right on top of that, how do you get the first bead back? Well, you can't, not right away. You have to pop the top bead off first just to reach the one beneath it. The stack works exactly the same way. The first item pushed into the stack is literally the last item to come out.
You know, we can also visualize this as a really bustling inter-office bureaucracy. When a new function is called, it's kind of like sending a worker to a brand new desk. They need an envelope containing their specific instructions, their materials, and, crucially, exactly where to send the results when they're finished with their work. So let's peek inside one of these inner office envelopes, our stack frame. What exactly does the receptionist keep track of in there? Well, it contains the function's local variables, right? Those belong only to that specific desk. It contains the arguments that were passed to that function. It holds the saved frame pointer, or SFP, which basically remembers the base configuration of the previous desk. And finally, the absolute most critical piece of paper in the whole envelope, the return address.
The return address is for sure the true magic trick of the stack. See, the processor only reads one single instruction at a time. So once a function finishes its job, the current stack frame is gracefully popped off our string of beads. Then the return address is read to flawlessly restore the exact context of the previous stack frame. The program's execution pointer, the EIP, just jumps right back to where it left off, exactly as if it had never stepped away to run that function in the first place. It is this intricate, perfectly choreographed ballet of data.
And so we return to Arjun in his room. He now fully understands this magnificent 5-story building of memory architecture. But looking at this beautiful rigid system leaves us with a highly provocative thought. If our entire digital world relies on these invisible, delicate papercraft mechanics flawlessly passing variables and stack frames around, what happens when a clever hacker learns to fold the paper differently? What happens if they manage to overwrite that crucial return address on the stack and point it to their own malicious code? Well, my friends, that fragile edge is exactly where the true art of exploitation begins. I hope this explainer has illuminated the elegant structure of memory for you and shown you why understanding the foundation is just so absolutely vital. Until next time, keep asking brilliant questions.